Thanks a lot to the organizers for the invitation to this very nice conference and for the hospitality here at Boston College. So everything I'm going to talk about is joint work with Julius Ross from Cambridge and Matej Thomas from Nancy. And so I'm going to talk about Mariana, what I'm going to say, Giesecke moduli spaces on higher dimensional manifolds. So the following notation will be used. So X will always be a projective manifold over the complex numbers, the dimension of which I will denote by D, and I look at sheaves of fixed rank R and Chern classes, say C1 up to CD, which I sort of sum up in a vector C. And so in order to construct moduli spaces, one has to fix a semi-stability condition, and the stability condition I'm looking at is the traditional one, so Giesecke stability, and this depends traditionally on the choice of the class, of a class in the ample cone. So I take a class in the ample cone of X, and then for E, a torsion-free, well, it doesn't necessarily have to be torsion-free, but this will be part of the semi-stability condition. I look at the Hilbert polynomial with respect to H, and just to remind you, so this is chi of E tensor OX MH, and by Riemann-Roch, this is, or it starts with the rank times m to the d factorial plus, okay, let me write one more term, so this is C1 of E times H to minus 1 plus R times the tot 1 of X times H to D minus 1. So that's the coefficient in front of m to the d minus 1 divided by d minus 1 factorial plus higher order terms where the coefficients involve the Chern classes of E and powers of H. Right? And so, given this, I call such a torsion-free sheaf E semi-stable or semi-stable if and only if for all non-trivial proper subsheaves of E, I have the following is less than or equal to this normalized Hilbert polynomial of E, and so this is meant to be as a polynomial, so you can ask this to hold for arbitrary large numbers. If you plug in arbitrary large numbers n into this polynomial. Why don't you do lexicographic ordering, which is the same? And so let's shortly look at this. We will come back to this. Why do I divide by the rank? Well, of course, I mean, sort of this kills, it doesn't really kill, but sort of makes this first term equal if I compare these two. And so the first interesting term is essentially C1 of F divided by the rank of F times H to the D minus 1 compared to C1 of E times H to the D minus 1 divided by the rank of E, and this is what we would usually call the slope. And if that's the same, you look at higher order terms. Okay, no, lower. So you go down. And then once you look at all these sheaves, which are torsion-free and semi-stable, these form a bounded set, and you can construct the moduli space of Giesecke semi-stable sheaves where you measure semi-stability with respect to H of this fixed rank and fixed Chern classes, and I would usually suppress these R and C, which I consider fixed for the rest of the talk. So this is modular space of H, semi-stable sheaves. So in these form, while very interesting varieties, they have been studied a lot, and so my main point here is to investigate the dependence on this parameter H, which we chose from in order to define this notion of semi-stability and semi-stable, and which is sort of a priori artificial, right? So you want to parameterize torsion for sheaves on your variety X. Okay, you have to fix some topological invariant, but then in addition you have to fix the semi-stability condition. Of course, you could look at the stack of all of these, but okay, now to do that. Yes. Okay, so question A is, how does DSSH depend on H in the amplicone? And we've seen this in Aaron's talk, that in the case of surfaces, so let me comment, so in the case of curves, there is no choice. You don't have any choice. There is a fixed notion of degree. And then on surfaces, this has been studied a lot, say, in the 90s, and a sort of beautiful picture has emerged where you divide the amplicone into a number of chambers given by rational linear walls. There is work of Matsuki and Wentworth, which realizes the two different moduli spaces under these Chern class conditions that we have to, in order to make it irreducible and normal, basically as two different GIT quotients of the same space. And now we also know how it's related to Bridgeland stability, thanks to the work, the recent work. Okay, so as I said, in the surface case, this is very beautiful and we understand a lot. However, also very early on, people discovered that as soon as you move one dimension higher, so into an arbitrary dimension, or let's say dimension 3, problems start to appear. And let me present you this example of Alexander Schmidt I keep telling people about since I learned it in 2008, which is very nice. So you look at the general member of the linear system on P2 times P2 3, so it's a bi-degree 3 hypersurface inside P2 times P2. And then, okay, you look at the amplicone, or the Neff cone, and this is how it looks like. It's just a quadrant. So the first one. So you basically have a one-parameter family of ample bundles, so H1 and H0 are not really ample. Ignore that, and you can look at this variable family, which I denote like this. So I look at, I walk along this segment from H0 to H1, and so I want to understand how the moduli spaces change. So I don't really care about moduli at the moment. So I look at the single sheaf. So then you can construct a relatively explicit rank 2 vector bundle E on X, which has the following property. So you look at this single vector bundle and you check whether it's semi-stable in the sense, so let's say here, and then you move along and you check all the subsheaves, and you check whether this inequality is fulfilled with respect to h lambda. So, and the at first very surprising thing is that if you do that, you find that AE is h lambda stable. So this means we always have this strict inequality in here for something like lambda less than 3/2 minus 1/2. And the interesting thing is the square root of 7. Which I call lambda critical. It's h lambda semi-stable. So suddenly I find a subsheaf inside, so F inside E, where I get equality here. And then if I move beyond the critical value, it's unstable. So the same sheaf, subsheaf, will violate the inequality. So E is not h lambda semi-stable for lambda bigger than the critical value. So
why is this pathological? Why is this already in the surfaces you have such things?
Not rational.
It's not rational.
Oh.
Yeah. So the point is, okay, I try to emphasize this. So in the surface case, you have some similar picture. You have your ample cone, but you divide it into rational chambers by essentially linear rational walls. And here you find an irrational point, and since the Picard rank is 2, it doesn't depend on the segment it shows. I mean, you know better. I mean, the way it is irrational, there is no rational point, and there is no line bundle attached to this R divisor. Of course, in the minimal model problem, we nowadays know how to deal with R divisors, but in this modular theory a priori, it's a big problem. I will comment on that.
Are there examples known where the stability locus isn't even polyhedral? I mean, could you a priori get like some kind of non-polyhedral?
Yeah, so I mean, okay, I will not really talk about this, but if you think about this, this should really be in higher, so if you go to higher Picard rank, this should really be cut out by quadratic equations. And so why is that? So at first it seems surprising, but if you look at this, you see that this is not a very special example. It's actually a pretty generic thing. So actually the subsheaf that violates the equality here, as I said, this is lexicographic ordering. The change already appears in the first coefficient here. And you see, if you vary this part, you vary it non-linearly in H. So you really expect this to happen. Right? So, I mean, if these two, that's linear. But not in higher dimensions. Okay. So why is this a problem? Well, many of the techniques you use in dimension 2 to compare the moduli spaces on two sides of the wall, they involve a moduli space constructed for the polarization on the wall. But here, there is no such thing. Yeah? So, on the other hand, yeah, so let's look at this this polynomial again. I mean, that defines the semi-stability. Of course, the problem is the left-hand side doesn't really make sense for if H is irrational. On the other hand, this polynomial still makes sense. So given the sheaf, you can still look at this polynomial, and for every m you will get in general irrational number, and given the subsheaf, you can still compare the two numbers and ask for an inequality. So this is an observation. So the first problem is that H lambda is in the real span of the ample cone without coming from a line bundle. And the second thing you note is that somehow formally you have something. So formally the right hand side of Riemann-Roch and with this semi-stability as a notion still makes sense for any h in the real span of the ample cone. So it doesn't, the theory doesn't really break down altogether, only you don't know what to do. So, and that's really leads to the second question. So as I said, in the surface case you use a moduli space sitting, so where the moduli, so the semi-stability condition is computed using this polarization on the wall to compare the moduli spaces left and right. So the natural question is question B. So does there still exist a moduli space? So does there exist a maybe even projective moduli space for, so let's give it a name already, even though we don't know yet whether it exists, for h in the real span of the ample cone. Yeah, and actually if you look in the, so if you think about this in terms of scalar or complex geometry, well, it's not that bad. It's in the real span of the ample cone, so it's still a scalar class. And so in this sense, it's very closely related to a question raised by Turing about the existence of moduli spaces of semi-stable sheaves on an arbitrary compact scalar manifold. Right? So this definition with Riemann-Roch makes sense in an arbitrary compact scalar manifold. In general, the question whether the moduli spaces exist is wide open. Even in the surface case, you have you need to know powerful algebraic geometry to solve it. Okay. So let me tell you about the results we have concerning these two questions, and let me focus today, because it's easier to formulate, on dimension x equals 3, which is the first interesting dimension, and also maybe the one of the most interesting ones, because if you think about Calabi-Yau threefolds, then some virtual dimensions are 0 and you expect to be counting things. So maybe that's also the most interesting dimension. So the results are the following. Essentially, we can solve these questions. So theorem 1 says that, well, I mean, solve, you know, in a philosophical way, in the sense that, okay, I will try to explain how the fact that this is an irrational point really is not such a big problem. I will not tell you anything about how to compute the change of invariance between two given moduli spaces on a given Calabi-Yau threefold. Yeah? So this is not my aim. So I start with two ample bundles, really. So these are really ample bundles. And then the statement is the two moduli spaces M p sigma H1 and M p sigma H2 are related by a sequence of GIT flips. And this is really sort of this is the general statement. So what does it mean? So what does it mean? I.e., we will construct a master space. So there exists Z, an affine scheme. You can also do it on also construct a projective scheme, but we go as higher as possible. So an affine scheme with a G action where G is a reductive group, so it's a product of GLNs, and U1, U2, two G invariant sub schemes of my Z, such that uj, GIT quotient by G, is exactly the moduli space that you're looking for. Right, so this is, so the statement is you construct a big space for which you can construct these two moduli spaces as GIT quotients with respect to the same group, but with different linearizations. And then, yes?
What about the connected component of Z and the intersection of U1 and U2? Do they always intersect?
Well, I mean, okay, that's one thing one problem in the high dimension that this does not solve is that you don't have these sort of irreducibility theorems for high or low Chern classes. So I mean, this is most interesting if you go to a wall where you know that somehow you have some semi-stable object, properly semi-stable object on the wall, but you have sort of common stable objects on both sides. So in this situation, this says that you have a component which is sort of the two sort of main components are birational, and then you might also, you might contract things. I mean, this is not something you can avoid. I mean, there are examples, and this basically just says that that there is some way to relate these, and this sort of generalizes the surface results of Matsuki and Wentworth.
I mean, are U1 and U2 open in Z?
Are they open and are they dense?
So what you can say is that they are, so the closures are union of components. So if I take a closure of U1, then I get a union of components, and I take a U2, I take a closure of components, a closure of U2, I get a union of components of Z.
Right, he's trying to avoid a vacuous statement where Z is just a disjoint union of two things, U1 and U2.
Yeah, but he doesn't, I mean, it's if, the statement is if they intersect.
I see.
If they, so I mean, okay, if they intersect, then somehow it's really the statement that you on this component you have a variation of GIT. I mean, sort of, okay, I mean, you have to think about sort of components that have nothing to do with each other, then okay, this you can of course construct this. I mean, we will see how this is constructed, and then maybe the question is sort of answered. I mean,
can you say that if there's a sheaf that's semi-stable for both, then the two components intersect? Like, can you
yes.
Okay, so then it's not vacuous.
Then it's not vacuous, right?
Okay, maybe there is an even more interesting statement is the second one, that if I take any point here, so this was the point that created the problem in this example, then I can construct, or we can construct a projective moduli space and for H semi-stable sheaves. Right? And the example shows that these moduli spaces are really new in the sense that, well, because of this special sheaf E, we know that this moduli space you construct for this critical value is really not one of those moduli spaces on the left or on the right. So, let me, in the next section, which is sort of slightly technical, explain the technology we introduce to deal with this problem and to circumvent really this non-rationality. It's not, so in a certain sense, this really doesn't tell you anything about the general problem of constructing moduli with respect to Kähler forms. This was our first hope, to really do Kähler geometry, but this seems to be very hard. Basically, you reformulate and use a trick to move around the wall.
What
this
is the relation between the moduli space for the irrational value and the moduli spaces on the two sides in this example?
Okay, in this example, actually,
Do you have a morphism?
well, in general, you have, we have morphisms. If you go to the slope, if you pass to slope moduli spaces, they fit into a sort of flip diagram. In general, this is also related to the others by certain GIT flips, but it's not that easy. I mean, you have to go through really a sequence of things where you have to change the polarizations and maybe also sometimes really go to some sort of twisted Giesecke standing stability. This is already in the surface case. It's not that direct. Okay, so 3 is what we call multi-Giesecke stability, which is probably not really new, but because it's a very simple-minded thing. And this starts with a number of line bundles. So I just give myself J naught ample line bundles, which I consider, so you see later, in the end, in this variation problems, these are sort of fixed. And I give myself the same number of real numbers, so, and these will be variable. So the idea is to push the variation into a different sort of direction. So I not sort of vary age, but I vary some numbers. Okay, and then if E is again a sheaf, well, it's assumed to be torsion-free, because that's what I'm going to be looking at, I define P sigma of E of M, it's going to be a polynomial, and already you see I dropped the L's, just to be the weighted sum of the Hilbert polynomials with respect to the individual line bundles. So this is so if you plug in now the vector 1, 0, 0, 0, 0, you will get the Hilbert polynomial with respect to L1, and so on. So this somehow formally interpolates between all these different Hilbert polynomials. And as you expect, I call a sheaf L sigma semi-stable if, again, for all non-trivial proper F inside E, I have this inequality. Right, so this is just a formal, relatively formal definition. But we will see that it is sort of enough to deal with this problem. So there are a couple of things you notice. So the first proposition is that, okay, sheaves which are semi-stable form bounded families. And if you look at the variation in this setup, so then, as said, I consider the L's to be fixed and the sigma to vary. So I look at R bigger than 0 to the J naught copies. This has a linear rational chamber structure let's put it like this, witnessing the change of semi-stability. Yeah, you can somehow see how this works, because if something, this is because you shifted sort of the variation in front of the polynomial and also on in the coefficients, so it's really a linear variation in every step, and not, whereas here, in the first coefficient, you had something which was very non-linear. So this is basically just, this is so relatively easy to see that. Yeah, so the question is, so this is relatively formal, what does it have to do with questions A and B? Yeah, and so this I'm going to explain next. And one of the key points is the following proposition, which I proved earlier with Matei, which somehow was surprisingly wasn't known before, seemed to be new, although I'm very surprised that this is so. So if you look at the smooth projective d-fold, then the map, which takes, so let's call this P d minus 1, an ample class into n1 x sub r, so this is, so these are curved classes, and okay, what can you do? You can take a class, and you can take its d minus first power, right? So if it's an actual ample bundle, then the curve class you get is the one of a complete intersection curve in this, for this bundle. This is an open embedding. And we discussed this over lunch yesterday. At the moment, we don't really know so much how the image of this map looks like. And okay. Okay, so this is a general statement about cones or subvarieties of projective manifolds. How is it related to the problem? This I will explain next. So how is it related? And this is, the next proposition really uses dimension 3. So maybe I should, before stating it, say what we want to do. So I claim that this setup with this multi-Giesecke stability is enough to capture the, or to produce polynomials that I get as Hilbert polynomials with respect to real ample classes. Right? So I said that if I have a real ample class, I can still write down this polynomial with real coefficients. So this is just a polynomial. And then I can try to find Lj's and sigma j's on my x such that I get the same polynomial when I write down this. This is at first formal. Yeah, and this is what the proposition says. So that H be an element here. And okay, I set J naught to be, it's pretty big, so it's 4 times rho x plus 1. Then there exists ample bundles L1 up to Lj naught. So these are now really ample. These are really bundles that have the following property. If I look at the set of classes that I reach with this, so let's see. So this is this following set. I look at sum sigma j Lj, comma sum sigma j Lj squared. And the important thing is that it's the same sigma. and I'm allowed to vary sigma j in here. So this is an open neighborhood of the point h comma h squared inside the ample cone times this space N1. Yeah? So this means I cover, so if I'm allowed to vary this, and I have enough bundles, I cover enough classes to, so let me draw a picture somehow. Okay, here is amp, and then N1, and then it really looks sort of like this. So this is sort of, I have the image, so this is the image of identity times P, so in our case it's P2, yeah, and then I'm here, and then I reach an open neighborhood of this, and in particular I reach, now I can restrict to this part, I can cover an open neighborhood of this. Yeah, so this means, so in this way, I get open neighborhood UH inside the ample cone R such that the following holds, such that A, for all H prime in this neighborhood, so in particular H in all other real classes, there exists a vector sigma in the space of parameters, called this sigma, such that the Hilbert polynomial with respect to H prime, which was just this formal object, is now the multi-Hilbert polynomial with respect to this, collection sigma and this fixed class of line bundles L1 up to Lj. Right, so this means, so this is now M. Let's say this sits on some sort of wall. Yeah? I can cover an open neighborhood of this, and I can write every polynomial which arises from these ample classes in this way with fixed L and varying sigma. So I've pushed the whole problem of variation into sigma space where the variation is linear. And so one nice consequence of this is that you can go one step further. So please note that at the moment, so at first, I solve this sort of essentially numerically. I mean, you write down the solution. I mean, you write down what you have to do. This still has real coefficients. But then, because of proposition 3, the way semi-stability varies in sigma, it's linear rational, you will also find a rational point inside this space which does the job. So this is an elementary observation using proposition 3.
So this proposition here is, how much algebraic geometry is this? Is this just something, is this mainly about something about quadratic forms and cones?
Modulo the proposition before, which is really Lefschetz and algebraic geometry. So this is almost, yeah, so elementary. Yeah. And also let me comment, so this is really dimension 3, but the problem is if you do dimension 4, you also need, so you have L squared, and L cubed, and you understand L cubed good because of this proposition, but L squared somehow is there in the middle, and you don't know what you reach using powers of things in the Ampere code. So, at least at the moment, I don't understand. Okay, so this is B. Because of proposition 3, we have for all H prime in this neighborhood, there exists a sigma in Q, J naught copies, such that H prime Giesecke semi-stability is equivalent to L sigma multi Giesecke stability. Okay, so you might say, okay, this is all very nice, but it's formal, but what have I gained? I've gained a lot. So this H prime Giesecke semi-stability a priori is just, you produce a polynomial out of your sheaf, but you have no idea how it's related to Hilbert, to Euler characteristics, to sections, to cohomology. Here, you have a weighted sum of things you can understand. So here, now you have really some control, and you have geometry in the sense that you have these J-naught line bundles, you can do sort of meta-Ramanathan theorems, you can restrict, you can produce curves out of this, and so that's very nice. Okay. So what do I have to do? So let me sort of sum up where we are at this point. So I pushed the problem and I explained how to reformulate the problem. So two problems, A and B, in terms of this L sigma stability. And the only thing I now have to do is the following. So let's do question B first. Question B was, do these moduli spaces exist? So I just told you that it's equivalent to L, sigma semi-stability, so I just have to write down or construct a moduli space for this semi-stability condition. And better, since I have this sort of uniform cover, I cover a lot of ground using just a variation of the sigma. In order to prove this variation statement, I just have to construct a moduli space, or the moduli spaces, assuming L fixed, but sort of uniform in sigma. So if I can exhibit a construction which is sort of uniform in sigma, then I'm sort of using GIT, I will at the same time prove the variation, and this is what we do. Okay, so this is for constructing moduli spaces using, so for this multi-Giesecke semi-stability conditions. Okay. So for the rest of the talk, L1 up to Lj naught are fixed. You can think about those whose existence I claim here. And then, okay, the first proposition is that you have boundedness, so the set of sheaves that are L sigma semi-stable for some sigma in sigma is bounded. So I have sort of boundedness uniformly over this sort of quadrant, which is, not that difficult to believe because really it's almost a compact set, and if you think about the slopes you can get, the slope functions you can get from that, they will form a compact subset of the movable cone. So this is almost follows from traditional boundless statements. So now I'm going to start constructing the moduli space. Okay, so any sheaf that is bounded with respect to any of the some parameter I'm looking at is inside a bounded family. So this means there exists an n such that all L sigma semi-stable sheaves E, they are n-regular with respect to all the line bundles involved. That's just consequent of boundedness. So if you don't know what n-regular means, this in particular implies that for all n bigger than or equal to n, all such E have the following property. If I tensor them with any of the Lj to the n, they are globally generated. So H naught E tensor Lj to the n X subjects onto E tensor Lj to the n, or so how should I think about this? I twist the other way, so I have H naught E tensor Lj to the n tensor Lj to the minus m. This subjects here. So I realize each E as a quotient in J naught ways. So right, so I now have this. Yeah, so from J runs from 1 to J naught. So I have J naught representations as a quotient, and of course they all give the same E. Right, so that's too much information. So I have to relate these different quotient representations. Yeah, so for this I do the following. Yeah, so maybe I should comment up to this point. This is exactly what you do when you construct the moduli space for one polarization. Yeah? You choose one of the Lj's and you do this, and then you go on. And somehow now I have to avoid, remembering too much information and constructing sort of J naught copies of something. So I have to see how these quotient representations are related. And this is also easy. So I set Hij to be H naught Li minus n Lj n, and then you get multiplication maps which tell you exactly how these quotient representations are related. So I can do H naught E tensor Li to the n tensor Hij, and this will map to, using multiplication, H naught E tensor Lj to the n. So this means, what have I done? So using regularity and boundedness, out of a single sheaf, I've produced tons of linear algebra data. Yeah, I produce, so for example, if I do I equals j equals 1, these are the multiplications map from H naught E tensor L1 to the n to H naught E tensor L1 to the n. And this is exactly what you use. So this is, in a sense, the Plücker embedding of, or this is like a Grassmannian embedding of the quad scheme you use to construct the standard moduli space. And now I have all of them together, plus sort of these multiplication maps with Ij different, which interrelate them. So, and of course, you cannot remember all of this data, so you have to organize this. And this is where quivers come in. So, quivers just organize lots of linear algebra data. So you get a representation of the following quiver. So phi E of the following quiver Q. So this quiver has J naught rows. So let's do, and then let me do it for J naught equal 2, and then you get the idea. So you have two sort of Kronecker quivers, and then you have the diagonal multiplication maps where you label H21, H12. Yeah, so you should, this mean, you can also say, what is this? This is just, okay, you compute the dimension of this. This is small hij, so we have hij linear maps from here to here. And so this means you have a representation of this quiver. If you have a third row, you have to add all the diagonal maps you can do from left to right. So this means, out of this sheaf E, I get a representation of this quiver.
You are choosing N and M. N was mentioned here, and M was chosen. Is this the same N as before?
Yes.
Oh, N is...
N, as soon as the sheaves are N regular, I can do this.
But what about the choice of the two integers, N and M?
So I mean, sort of for every n bigger than or equal to n, I can get the representation of a quiver, and what changes is the dimension of the vector spaces I put here, which you can compute. So these are just the dimensions of these H naughts, which you can compute from the...
I can't see the exponents there.
Excuse me? No. Yeah. So I will later sort of claim that, you know, for if I fix n and m big enough, then something happens. So for at the moment, for each n and m, I get representations of this quiver. So the fact is,
So these spaces will be 0.
well, if n and m are big, then none of these spaces
M
can.
is always much bigger than
N, yeah, so let's see, n, yeah. So I mean, let me write the next. So for 0 small compared to n to m, phi from n regular sheaves to the category of representations of this quiver of dimension vector which you can compute from the Hilbert polynomial is fully faithful in many. So this means that it recovers the sheaf, and I can precisely say which representations come from sheaves. And there's a canonical way, I mean this is really work of King and Alvarez Consul, how you can reconstruct the sheaf from the representation as a module over the path algebra of the quiver. Okay. And notice, so I come to the end soon, so notice that, and this is very, very important, up to this point I have not talked about stability. This is just a question about regularity, and you know, everything I'm going to talk about, you know, everything is in a bounded family, so this is, you know, stability entered here, but then, now I'm on this side. Okay, of course now the real work only starts, because, so this is theorem 4, and this is really the technical art of the paper. So there is a natural. Okay, so this is not the theorem yet, but I have to say one more word. So there's a natural notion of a sigma semi-stable representation of Q. Right? So there's a theory of semi-stable representations of a quiver, and in this case, and it depends, so the group you're looking at is a product of GLs, the characters you can choose are just central characters, so they are numbered. Basically, the choice you have to do is a set of J0 rational numbers. So you take, as the J0 rational numbers, you take the sigma you already have, modulo, there was a small line, you transform it into something, and then you do weighted counts and fractions of dimensions of the vector spaces you put here, and you have the sub-representation. The corresponding number has to be big or small. Yeah? So there's a natural notion of a sigma semi-stable representation of a quiver, and for n large compared to n large compared to p and to 0, this phi is compatible. With L sigma semi-stability on the left-hand side and sigma semi-stability on the right-hand side. So this means for any stability condition you ever want to consider in our problem, this map is perfect. No?
This is not hidden in any of the work of King and all these people?
Well, I mean, probably, I don't know. I mean, so the point is, King used this Kronecker quiver, which appears as one of the rows, to construct the moduli space, and essentially we follow his proof, but you see, the main point is to estimate sections using slopes, and here we have this weighted count. So essentially we have some sort of adapted Lippertier-Simpson estimates, and we really do it step by step. And it's, the strategy is the same as King's, but you have to really do look at this weighted counts, which somehow is really, it's messy, but in the end you can do it. So it's not there. In a way, no new ideas are needed, you just have to push hard. And so now we're almost done, because now I've moved everything to this side. I know which representations come from sheaves. I know semi-stability is on two sides. And then King tells me how to construct a moduli space of representation of the quiver, and that's really close to linear algebra. This is somehow GIT in one of its purest forms. So I tell you, so the moduli space and sigma QD of semi-stable representations of Q of dimension vector D is constructed as follows. What is a representation of a quiver? Well, you choose vector spaces of the correct dimensions on each of these things, and then you look at linear maps as many as the arrows in your quiver tell you. So what do you have to parameterize? In the end, you look at linear maps. So this is, you look at a direct sum of linear maps from, C to the, let me be precise, the correct dimensions are given by the Hilbert polynomial tensor Hij to C Lj to the n. So these are the dimensions of these spaces. So L, this is n and this is m. And then here a product of GL's acts on this affine space, and then the moduli space is just the proj of not the invariance, but you look at covariance, where you have to sort of look at the character which is given by sigma. So sigma gives you a character, you look at all the functions that transform correctly, That's finally generated algebra, you do the proj, and that's the moduli space for quiver representations. And now we're done.
And this is for sigma rational.
This is, and okay, thank you. This is very important that sigma is rational because this gives me a rational character of the group. Otherwise, I just have a real character. Okay, then it could, maybe do something, but this really uses sigma rational. And now I'm in a position to look at phi. So phi gives a G invariant locally closed subscheme Y inside H. So these are the representations that come from sheaves. And then, because of the fact that everything is compatible, if I take the closure of Y and intersect it with the set of points which are semi-stable for this GIT stability condition, this is exactly the set of points I get from sheaf semi-stable sheaves. Right? So these are exactly the point I get from L sigma semi-stable sheaves. And then the moduli space M G S S sigma is just you take Y L sigma and you mod out by the group. And this shows I have this uniform construction of these moduli spaces. This solves the two problems. If I have two H1 and H2, they will both appear for different sigma same L. And if I have this real parameter H, I have also found a sigma L sort of datum which gives the same semi-stability condition, and this constructs the moduli space at the same time. And so this is, and then, so sort of this is problem B, and problem A, you set Z equal to Y bar. And this hopefully also answers the problems about the components. You really look at the things you get from sheaves, and you look at the things that come from semi-stable sheaves. Of course, you have problems if they don't intersect, but that's really not the interesting case. And use this Z as your master space. But if you want to, I can comment on that later. You can also do a projective version, but I mean, I think this affine thing is really a nice space. So thank you very much.